In part 1 on vertical navigation, we took a look at altimetry, all about understanding how the altimeter works in an aircraft. We change our altitude though by climbing or descending, but how much time and how much distance does it take to achieve these maneuvers? Let's find out. Hi, I'm Grant and welcome to class 13 in the GNAV series. In this second class on vertical navigation, we're going to be looking at the actual maneuvers we use to change our altitude, either climbing or descending. This mainly consists of some simple speed, distance, time calculations, but there are a few little tricks to watch out for. So when we fly our aircraft around, we need to know how long in terms of distance or time it will take to change in altitude by a set amount. So if there's a mountain, for instance, 1,000 feet above our current altitude, and we're 5 nautical miles away from it, we need to be able to figure out if we will be able to climb above it in time, or if we'll have to fly around it or pick an alternate route. This is done by using speed, distance, time calculations, essentially the very basic velocity equals distance divided by time. The trick to watch out for though in aviation is we have to both consider the horizontal and the vertical distances. So for our horizontal calculations, we can say that our ground speed will be our velocity, and our ground distance will be the distance, and the time will give us a value in hours. And it's important to note that ground speed is our true airspeed plus any wind components. And if we have a headwind, it would slow us down moving along the ground, and if we have a tailwind, it would push us faster along the ground. For our vertical calculations, we can say that our vertical speed in terms of feet per minute will be the altitude change in terms of feet, and that will give us a time. And that time will be in minutes. So there's a difference between the minutes and the hours, which we'll just take a look at now. We can combine those two equations using that common factor of time. So we'd have our ground distance over our ground speed equals the time. We've just rearranged the speed, distance, time calculation. And that time will also be equal to the time that we spend changing vertically. So our time is the common factor, altitude change over vertical speed. But this was feet per minute that we were using, and this was nautical miles per hour. So we're going to be, one answer will be in minutes and one answer will be in hours. So we basically have to convert one into minutes or one into hours. I think it's easier to find the knots in terms of knots per minute instead of knots per hour, the ground speed. And the way to do that is basically multiply by 60. So you get an equation which is ground distance times 60, or 60 times ground distance over ground speed equals the time, and that equals the altitude change over the vertical speed, and that will be giving you a time in minutes. We can then use this equation to calculate either time or distance or speed, whichever is required to achieve certain altitude changes, which we'll look at in a little example. So here's the example. During a climb towards a VOR DME station, VOR DME station is like a radio beacon. VOR gives you the direction and DME gives you a distance. So the DME element of this station shows that we're 8 nautical miles away. The average true airspeed during the climb is 120 knots, and there's a 15 knot tailwind. When passing 5,000 feet, the rate of climb is 800 feet per minute. What is the estimated altitude passing overhead the VOR DME? So let's write down the equation, and it's basically an exercise in plugging in some numbers. So we have ground distance times 60 over ground speed equals time, which equals the vertical distance or the altitude change over the vertical speed. And then we would just plug in the numbers. So our ground distance times 60, that's going to be 8 times 60 over our ground speed. Now ground speed is the true airspeed plus any wind component. So this is going to be 120 knots of our true airspeed, and it's a 50 knot tailwind, so that's going to be added on. We're going to be moving faster along the ground. Think of it like the sail on a boat. That wind pushes the sail and it makes us travel faster along the ground. So that's going to be divided by 135 to give us an answer for time. And then we would use that time to work out our altitude change. That's what we're looking for. And we have our vertical speed, which is 800 feet per minute. Okay, so 8 times 60 equals 480 divided by 135, and we have 3.5 minutes. So time equals 3.5, or 3 minutes 30 seconds, and that will be multiplied by 800 to find the altitude change. So 800 multiplied by that gives us the alt change, and the alt change will then equal 3.5 times 800 for an answer of 2844.4. So that's the alt change, but we're actually looking for the altitude passing overhead the VORDME. So we simply add that on to 5,000, and the answer would be 7,844. So we need to talk about speeds in the climb and descent. There's a few to wrap your head around, and it involves a bit of principles of flight as well as a bit of instruments. So speed is calculated by sensing the static pressure and then sensing the pressure as we move through the air using something called a pitot probe. We'll get a value for our total pressure. We then compare the two, and we know that total pressure is made up of static pressure plus dynamic pressure, and we basically read the value for dynamic pressure. That's the added pressure that comes with us moving forward through the air. And dynamic pressure is made up of a half rho being the density and v squared being our speed. So we can calculate the speed from sensing our total pressure as well as having a value for our static pressure. This dynamic pressure is then fed into our speed instrumentation through mechanisms or equations if it's a digital speedometer, and we get an indicated airspeed, or a IAS. That's what we're actually reading on the instruments. If we correct for any known instrument errors, we then get the calibrated airspeed. So say you had a speedometer that you know is always 3 knots fast. Your indicated airspeed would show you 103 knots, but you know that your actual calibrated airspeed would be 100 knots. If we then correct for the compressibility effect that we experience at high speeds, basically the air coming in starts to compress together, so we don't get a very accurate reading for our indicated airspeed because the mechanism isn't sophisticated enough to deal with the compressibility effects. So once we correct for that, we get our equivalent airspeed, or our EAS. The final one to talk about is true airspeed. This is the speed that we're actually moving through the air. So as we climb in altitude, our density value starts to fall. If we were to maintain the same indicated airspeed, then our value for speed would have to go up to maintain the same output, because our density is falling. This number in here is falling, so our actual speed has to increase if we want to maintain the same numbers being displayed in terms of indicated airspeed. So think of true airspeed as the speed we're actually moving through the air once we correct for density changes. Because the true airspeed is the speed we're actually moving through the air, this is the one that we're interested in when we're talking about our climbing and descending problems. And then we would add the wind component on to get the ground speed, and so on. In the climb, we get into thinner and thinner air. The density drops as we climb. And that basically means that the engines start to perform worse. So as we climb, the average true airspeed isn't taken at the halfway point as you might expect, but we instead take it as a position that's 2/3 of the way along and use that for our calculations. In the descent though, we're not really relying on the engines, so there's no such issue with lack of power as we descend. So we can then take the average true airspeed from the expected halfway point. So an aircraft climbs at a constant calibrated airspeed of 200 knots between A and B, which are located 48 nautical miles apart. At A, the altitude is 8,000 feet and it is 10 degrees Celsius, and at B, the aircraft is at 26,000 feet with a temperature of minus 20 degrees Celsius. What is the flight time from A to B? So in this example, we've been given the tools to calculate our true airspeed, which will depend on the temperature at a certain altitude. Then we would use that true airspeed in our speed, distance, time calculations, that equation we saw earlier. The calculation for true airspeed is complicated, so you don't actually have to know the equation, and you can use the wonderful CRP5 computer, which I must confess I've completely forgotten how to use. It's been 5 or 6 years since I used it in the exams, So I'm going to be using an online true airspeed calculator, but I'm going to try and remember how to use and relearn the CRP5 computer. And then after I've done the videos in this series, at the very end, I'll do a CRP5 video. Anyway, we're climbing, so we're calculating the average true airspeed at 2/3 the distance. So we've got to work out the average position and the average temperature at that 2/3 position. So we're climbing from 8,000 feet to 26,000 feet, which is an alt change of 18,000 feet. And 2/3 of 18,000 is 12,000. So then we would add that on to our original 8,000 to get the value of the altitude at 2/3 of the distance. So 2/3 of 18,000, 12,000 plus 8,000, that's going to be 20,000 feet. So we're looking at 20,000 feet for our TAS 2/3 position. We also have some temperatures, so we're going to take the average temperature. Temperature change, it goes from 10 degrees Celsius to minus 20 degrees Celsius. That's a 30-degree drop, and 2/3 of the way it's going to be a 20-degree drop, and a 20-degree drop from 10 is minus 10. So you would use those values to calculate the true airspeed at 2/3 of the distance. Yeah, you would put that into your CRP5 computer somehow, I can't remember, but I did it on the online tool, and I got a TAS of 282 knots. You might get something a bit different if you actually know how to use a CRP5 computer, but it's going to be around the 280 mark at least. And then we use our equation. So ground distance, I'll just give it GD, times 60 over the ground speed, GS, equals our time. And do we even have any vertical speeds or anything? No, so we're basically just looking to find out this time. That's what it's asking for us, the flight time from A to B. You don't actually then necessarily need to multiply it by 60 because we can get a time in terms of hours, but let's just keep it simple. So ground distance of 48 multiplied by 60 over our ground speed, which is going to be, in this case, we don't have any wind information, so it's just going to be our true airspeed of 282, and that'll give us a time. So 48 multiplied by 60 equals that, divided by 282 equals 10.2 minutes. And if we multiply the 0.2 by, well, that second number by 6, we'll get the seconds. So it's going to be 10 mins and 12 seconds. So we use gradient a lot to define how steep a slope is that we have to climb or descend in. And it's basically the vertical distance, the altitude change, compared to the horizontal distance, the ground distance. Both distances will have to be in the same units, and the easiest is to convert the nautical miles into feet. And the conversion is 1 nautical mile equals 6076 feet. You can also think of gradients in terms of speeds. So you would have a horizontal speed and a vertical speed, because it's just the distance with an added time factor, but the time factor is the same between both, so you can do it with speeds as well. The gradient is the vertical over the horizontal. So in terms of percentage, we just divide the vertical by the horizontal, but to get it into the percentage form, we multiply by 100. Nice and easy. For the angle, we use a bit of trigonometry, as we have an opposite of this angle, the altitude change, or the vertical distance, and we have an adjacent, which is the ground distance. And again, these will both need to be in feet. So we can say that the tan of the angle equals the opposite, the vertical, over the horizontal. You can also use the 1 in 60 rule for these calculations. So the 1 in 60 rule basically states that the tangent of very small angles is approximately 1/60th of that angle, which means that basically you don't have to use a scientific calculator when you're flying in the air and doing this stuff actually whilst you're flying. So I'll just show you. So if we're looking at small angles, we're talking like 1, 2, 3 degrees. So let's take 2. So tan of 2 is 0.0349. 0.0349. But if we just take 2 and divide it by 60, we get 0.03. So we're a little bit off, but not too far. And then if we did the same with tan 3 degrees, 0.0524. And 3 divided by 60, 0.05. So they're not too far off, and it's a good estimation. What you can then say is we can basically ignore this tan and say that the angle divided by 60 is equal to the vertical over the horizontal. And then by rearranging, we can say that the angle is equal to the vertical times by 60 over the horizontal. You can then see that the number up here is 60 and the number up here is 100, but it's the same equation. So this value, the number value for this angle, will be 60% the number value for our percentage, or this will be 1.6 the times. So we could say that the percentage in gradient will be equal to the angle multiplied by 1.6, or the angle is the percentage multiplied by 0.6. Handy conversion this. So let's look at an example of gradients. So what rate of descent is required for an aircraft to descend a 5.7% slope at a ground speed of 120 knots? So we can just use our gradient equation, bearing in mind that we will need to convert from feet. We're looking for a rate of descent which is in feet per minute, and our ground speed will be in nautical miles per hour. So we need to convert that into feet per minute first, and then we'll be able to figure out the answer. So our percentage terms gradient equals our change in altitude over our change in distance. I know we're dealing with speeds, but if we just both give them the same unit of time, 1 minute or so, then that means we're going to cover a triangle of those 1 minute distances. Hopefully that makes sense. We're looking for our rate of descent, or our vertical change over time, over our horizontal distance in terms of time, which is our ground speed. And we also have to multiply by 100, sorry. So 5.7 equals our rate of descent times 100. We'll divide that by 100, and we'll get our rate of descent over the ground speed, which is in 120 nautical miles per hour, remember. So we're going to have to convert this 120 nautical miles per hour into feet per minute to get a rate of descent that's also in feet per minute. And to do that, 120 nautical miles times by 6076 will give us an answer in feet per hour. So we've got 120 multiplied by 6076. Get some mad number there, 729120. That's every hour. So if we divide by 60, we'll find out what it is every minute. 12152 feet per minute. Okay, so 5.7 divided by 100 is 0.057, and then we'd multiply it by this and get a rate of descent, which is 692.7 feet per minute. Due to a bit of a quirk in the units that we use, the nautical miles and feet as well as minutes and hours, there's a much easier equation that can be done in the air if needed and gives a good approximation of the answer. It's basically far quicker to use as well. So if we're looking for a rate of descent or a rate of climb, let's call it a vertical speed, we can just multiply the gradient by the ground speed. And we don't have to do any converting from feet to nautical miles to feet, or minutes to hours. Just by pure quirkiness of the units that we use, nautical miles and feet, it makes this calculation very easy. So in that previous example, we would have 5.7 multiplied by 120. So 5.7 multiplied by 120, 684. 692, 684, pretty close, which is pretty good if you're in the air. We're only 8 feet off, really. And that's like a very small change to actually notice when you're practically flying. So if I was in the air, for example, I would be very rough about this. to find a base rate of descent, then just adjust from there. So in this example, I say 5.7, that's roughly 6%. 6 times 120, that's 720 feet per minute, which is a bit off. You know, it's about 30 feet per minute larger than it should be. But I'd set 720 feet per minute, look and see what the trend is happening, realize I'm descending probably a bit too fast, and adjust from there. So in summary then, to calculate changes in altitude over distances, we use speed, distance, time calculations in the horizontal as well as the vertical. And because we're dealing with feet per minute and nautical miles per hour, we multiply by 60 on the horizontal side to convert everything into minutes. Important to note is that the ground speed is equal to our true airspeed plus any wind component. A headwind will slow us down and we take it off of the true airspeed, and a tailwind will speed us up and we add that on to the true airspeed to get our ground speed. The true airspeed is the speed that we're actually moving through the air, and it will increase in altitude if we fly a constant indicated airspeed, which is the speed that we're actually reading from the dial. The calibrated airspeed will be the indicated airspeed corrected for any known error instrument faults. And the equivalent airspeed is the indicated airspeed or calibrated airspeed corrected for compressibility effects, which we experience at high speeds. And we can calculate the true airspeed from the calibrated airspeed by using the altitude that we're at and the temperature, and then we plug those values into a CRP5 computer, or as I did earlier, a calculator online. We then use the average true airspeed to work out our ground speed for our maneuver. But in the climb, we use an average position of 2/3 of the way along due to the engine performance dropping off at high altitudes. And the descent, we don't have to worry about the engines as much, so we can just take the average point at the expected halfway position. Gradient is our vertical change, our altitude change over our horizontal change, our distance. And we can think of it in terms of percentage or angle. The percentage is the altitude change over the distance, multiply that by 100. And in terms of angle, we take the tangent of the angle, so we'd say tan theta equals the alt change over the distance, and we get a very accurate value for our angle. But we can also use the 1 in 60 rule, which basically states that at small angles, tan theta equals theta divided by 60. And then we would plug that into our equation, do a bit of rearranging, and we can use this as a good estimation for small angles. We can say that theta, the angle of the gradient, is equal to the altitude change multiplied by 60 over the distance. And because it's a 100 multiplier up here and a 60 multiplier up here, we can easily convert from percentage to angle, saying that the percentage gradient is equal to 1.6 times the angle gradient. And we can think of gradient in terms of actual distances, or we can think of it in terms of speeds, because that's just the distance with an added time factor to it. It's the distance over the time. When we are flying around though, we don't always have access to calculators to do these complicated calculations, and it can be a lot easier to use estimation that works due to the quirkiness of the units, just the fact that we work in nautical miles and feet and hours and minutes. We have a nice, easy to remember formula, and we basically take the percentage gradient that we want, multiply it by the ground speed, and that's the rate of descent we will need to achieve that percentage gradient. So if we wanted to descend down a 5% slope at 100 knots, we'd have to descend at 500 feet per minute.